I'm going to talk about our project that we were starting doing with Emil a couple of months ago. And basically, well, it's hard to talk about physics basically after such an expert. So there were two, Maciek and Michał. And I think, well, since I'm the organizer, I have not chosen my place to be in this at this hour to compare myself with them, but rather because it's the worst spot just before lunch. So I'm keeping you away from it. So I'm gonna try to be brief. But first, let me start with the motivation. So it's very good for me that actually I'm after Maciek, because this is gonna be topic related to simulation and of light, of state of the light after high harmonic generation. Something from attoscience. But also I'm gonna talk briefly about Hamiltonian simulation. In particular, how to do this in time-independent case, and then go to time-dependent case, and then finally to connect these two areas together. So, okay, this slide is definitely redundant at this point, but there was a Nobel Prize 2 years ago given to attoscience, and I'm going to talk about this process that, if someone didn't listen carefully, is basically the classical description, shining a very powerful light of low energy and then emission of very powerful photons. So this is high harmonic generation. Now, well, for various properties, the most, well, from various perspectives, the most important properties would be to look at the spectrum. This was actually the first thing to be discovered, that there is some plateau. It doesn't drop at relatively small harmonic order, but it actually increases. Well, it actually continues up to high energies. But now, well, historically looking at the field, well, it all started with the three-step model that Maciek explained. Then there is, well, Levenstein model, hard to say it differently, which basically is the basis for the Nobel Prize in some, at least from some perspective. Well, currently the state of the attoscience, the state of this of description of this branch of physics, well, it's complicated, I would say. I mean, there's ab initio, which also Michał was talking about a little, well, a lot actually, and analytical approaches. So what next? Well, the next thing would be to study physics, quantum physics, on quantum, well, devices, or at least using quantum properties of some molecules. So what actually was done by a group of Maciek and I guess a couple of other people was to translate the problem of one physical system to another physical system. So this is called analog quantum simulators. And basically, then some certain properties that we are interested in get transformed to another properties that might be potentially easier to reach. But that's one perspective, and what we want to do is look at this from, well, from digital quantum simulator side. So for us, instead of physical systems, we actually are not going to care what's inside. We would rather be interested in qubits and transforming this problem into matrices and see, well, what unitary matrices and eventually what would be the resources necessary to simulate such processes. So the central problem of our research is, well, to answer what would be the quantum state of radiation after interaction with matter. And well, looking at this from, let's say, a simple equation, there are harmonics here. So there is a driving field. There are higher harmonics which at first do not contain any photons. There is ground state of the electron, and then there is some there is evolution. Well, the disclaimer here is obviously that there are no quantum computers at this point. So what do we want to do with that? well, we don't want to simulate anything actually, but we would rather want to see what are the resources necessary to do so. So in particular, whether it's going to be possible to do when we're going to have 100 physical qubits or maybe 1000, and what are the depths, and how to do this in the most efficient way. So resource estimation, and from the other perspective, also development of framework. Because, well, at some point, well, hopefully we're going to have quantum computers. So what do we do with them? I mean, we don't just rediscover what to do with them at this point. Better start doing this now. This is well, this brings me back to quantum computing, and what do we actually want to do with it as soon as it appears. So the central premise with which the field started actually is simulating physics, and simulating physics, in particular quantum physics. So we call it Hamiltonian simulation because what you want to find is the unitary matrix that is exponentiated Hamiltonian operator. And then the goal is to find this unitary matrix on your quantum device. And well, it becomes even harder when this Hamiltonian is time dependent, as then you need to use time ordering, which is not, from mathematical perspective, maybe a very well operation, very well defined, but still it's necessary to do so. And then, well, how do we go? How do we approach our goal? Well, the first block that we actually need, the first, let's say, piece of the puzzle, is block encoding. So block encoding tackles the problem of what to do with your Hamiltonian once you have it. Well, once you have it, the problem is that this is not a unitary matrix, so you cannot just input it into the circuit because all elements of the circuits are unitary. So what do you do instead? Well, you just encode your matrix of interest into a bigger unitary. And then by this expansion, well, you tackle this problem and you don't care about it anymore, that this was not unitary in the first place. Well, one possible issue is that the norm of this H should have been A, that the norm of this matrix actually cannot be too large, as then the whole matrix will not be unitary anymore. So there is this there is the condition that the spectral norm of this matrix cannot exceed 1. How do we then, having this Hamiltonian encoded into some bigger unitary matrix, how do we approach this problem? So how do we actually perform exponentiation of the Hamiltonian? Well, the easiest, let's say the most natural way to approach this problem is via trotterization. Well, basically, you may look at this from two perspectives. So either your Hamiltonian is decomposed into some parts which are easy to exponentiate, or you exponentiate it with small time scales. And then you multiply all of this together. Hopefully, well, the errors would not be high. Well, actually, the problem is that errors scale quite badly. So not only there is the problem of commutator, but also there is a quadratic dependence on the time of your simulation. So now, well, can we do better? Well, it is widely believed that there is some lower bound that we cannot exceed, and this lower bound is actually linear in t. So if you want to simulate your system that's evolving, and if you want to simulate it on your digital quantum simulator, or let's say quantum computer, then the number of gates that you will need is gonna grow linearly in t at least. What we know is that, well, obviously there is caveat that there are some analytical solutions. So let's take, for example, harmonic oscillator, when you know what's going to be the state after, well, 100 seconds and 1 million seconds, it doesn't matter. But for generic Hamiltonians, it is believed that this result holds, which means that now the question is, how do we achieve that? Well, trotterization had this quadratic dependence on time, but there are better ways to do so. So one of them is quantum signal processing, and then basically the point of this scheme is to encode, well, first using encoding of your matrix, you want to process it, you want to apply some polynomial to this matrix. It turns out that d-degree polynomial can be, well, constructed on your circuit using d+1 rounds of single qubit rotations and then usage of this block encoding matrix, which in the form of the circuit looks like that. And it turns out that then you do have this linear dependence on time. Yes.
Well, I just don't understand how you encode A, because like if UA is going to be a unitary matrix, then A has to be a unitary as well. I mean, from the beginning, right?
Yes,
I mean,
that is true. Okay, that's a misprint on my side, let's say, because I've chosen this to be less general case. In the more general scheme, yeah, it's gonna need to be of slightly different form. Then we also gonna have this off diagonal terms, sure. Yes, well, the dependence on time is optimal, which is very nice. But the problem is that this scheme is hard to do for time-dependent Hamiltonians. Well, for trotterization, there was no problem because Hamiltonian, if you divide time into steps, well, for each of these steps, you can just change the matrix that you exponentiate. And this is not a problem. However, here we actually act on the, well, we want to obtain the polynomial, which is, well, exponentiated matrix A, and it's gonna be hard to find it from smaller blocks. So, so in this sense, from smaller times, let's say. So in this sense, it's not easy to apply the same scheme. And if you wanted to actually apply the same scheme, then there's gonna be additional error on top of that, which we don't want. So how do we go around this problem? Well, it turns out that actually it's an open question. There are a couple of known ways that how to overcome or try to overcome the problem of time-dependent Hamiltonian simulation. But for particular case of multi-periodic Hamiltonians, so for the case where your Hamiltonian is divided into terms out of which each is periodic with a different period, then by extending your system to higher, well, to another space, let's say is either Floquet or Fourier space, depending on who names it, then we can perform simulation with costs which will be linear in time, but at the same time additive, well, multiplicative in this time. So then also the error part is multiplied by time, which from some perspective is not the best maybe that you can achieve, but currently there are no better methods known. So yeah, this is basically the state of the art for multi-periodic Hamiltonian simulations. And yes, coming back to our problem, I remind you that there was state of the light, there was state of the electron, because we consider so far only one electron, and then there is unitary evolution which we want to approximate. Let me just pour water. It's complicated. So as I said, the basic elements of the puzzle are the ground state of the electron. Then what we also do is we treat the field in a second quantized formalism, because we actually want to find the state of the field afterwards. So we cannot just go around and use classical description of it or semi-classical description. And then there is also coupling, so electron dipole moment. So it is known that to obtain the matrix, or let's say unitary evolution of the field, you actually need to exponentiate this coupling term, so dipole and electric field, use time ordering, and then project it into the ground state of the initial ground state of the electron and the final state of the electron. And in this high harmonic generation, we treat the final state as the electron being also in the ground state because of this recombination in this classical picture. So how do we do this in the digital quantum simulator language, in the language of quantum computers? Well, effective Hamiltonian is actually composed of two parts. So one of them is dipole moment, the other is electric field, and they act on different Hilbert spaces. So for the electronic part, for the electric field part, we can use annihilation operators, and then approach our problem with the description in the Fock basis of n harmonics. So there is the driving field and all the harmonics that will get in which there will be photons after the whole process. But also, since, well, even if quantum computers will appear soon, they will not be of infinite size, obviously, and they never will be. So we need to truncate it to actually consider that some photon states, some number of photons in each mode is already effectively zero. So this is also another parameter that we need to add here. So using the scheme of multi-periodic time-dependent Hamiltonian simulation, we can estimate that with a number of modes, the complexity of this problem scales quadratically. The total query complexity, so by query complexity I mean here the number of gates that we would need to use to find the eventual unitary matrix, while there is very good dependence on the cutoff, so the number of photons in each mode, which is of square root type. So we hope that, well, at least in this regime, it might be easier to simulate something than by going maybe to higher modes. So there might be a trade-off of whether you want to go into higher modes or how many photons do you want to simulate in each mode actually. But also it's optimal because linear in T, and optimal because logarithmic in the accuracy that we also want to achieve. So by accuracy here I mean the distance between your unitary and the actual evolution. So plans. Okay, this is still work in progress because so far we have done this for the field. We have still not chosen the best modes or the best functions to describe the electron, because the problem here is that there is ground state of the electron, but in the process, well, in the middle of a process, electron also goes through continuum states. So in this continuum states, there are many ways to choose actually your functions, your wave functions, and some of them might be easier, some of them might be more accurate. We still don't know. There are a couple of ways to approach that. But also in the future, we would like to go into more than just a single electron, because this, what I just explained, is still for a single electron. And then we actually need to take into account also second quantization for electrons. And then maybe consider different initial states of the light, because, well, this is something that's already been considered in the laboratory, or from the point of view of a classical computation, is that, well, depending on your initial state of the light, some different properties might arise that you would want to have. Yeah, there is also a problem of other bound states, and seeing whether that would increase accuracy or whether that's not interesting at all. But this is something that's that I don't think is very well answered. Maybe Maciek knows more about it in the classical computing. So that might be useful to do this from the perspective of quantum simulators. Because they are more natural to actually include these bound states. Yeah, and also there is a question of how well can you actually try to simulate this problem using classical methods. So whether these quantum processes used on quantum simulators will actually be very hard to tackle, or maybe not so. And I guess the answer to that is that it is hard, because there are no known methods to actually do that using, well, at this moment, and people spend in this field more than 30 years trying to find the questions that we are asking here. So I guess the answer is that without actual quantum computers, some of these things will not be characterized. But, well, maybe I'm wrong. Never know. Okay, so to wrap this up before lunch, what we aim to achieve is evolution operator of the field, and in this form, well, in the form of a circuit. So we want to find an approximation to the actual evolution of the physical system, and as an initial state, we take a ground state of the electron, and then also initial state of the field. After projecting into final ground state of the electron as well, what we obtain is eventually what we should obtain is eventually the final state of the field. And then what you can do with that, you can either extract some observables from that, so then you can just apply some measurements, whatever you wish actually, but also it might be used as a part of your larger scheme. So suppose you want to use it for different things. I'm not so sure whether it's possible, whether it's useful or not, but maybe it would be good to discuss it with somebody of you. And then, well, we would expect that if quantum advantage is to arise soon for quantum computers, then possibly it would be in simulation of some highly non-classical processes. And for this, attoscience and high harmonic generation is perfect, I would say. And what we have so far is that the scaling in the photon number is rather well, but also we have optimal scaling in time and accuracy. And with this, I'd like to finish. Thank you for your attention.
Thank you, Grzegorz. Any questions before lunch? Fantastic.
Thanks, Grzegorz, for a nice talk. I have two simple questions. So first, at the beginning, I guess you cited work by by Dorita Faronov when you said about lower bound for the type complexity, right?
Sure.
So time-independent dynamics.
Yes.
Right. So are there some lower bounds for
Time dependent?
Well, I don't think there are actually, but for the processes that we are considering, so in this case, this is multi-periodic, which is nice for us because there are only 7 components in the total period, let's say, that governs the whole process. Then actually we can still obtain this linear dependence in time. So I guess at least for this particular case, the question is answered. I don't know anything about more general schemes.
Okay.
Any other question?
I have one question.
Wait for the microphones.
Did you make any numerical experiments with this method or any other simulation?
Yeah, actually, this is one of our plans. So obviously, I mean, given that based on our very rudimentary, let's say, very rudimentary approach, we said that this is going to be some 40-80 qubits that you might simulate the field with. So there is no way we can do this, obviously, either on today's quantum computers, or using exact simulation on classical ones. But what we would like to have is maybe some description of the process using fewer light modes. So then obviously it's not gonna be accurate and it's not gonna be useful for anything, but then we would actually be able to see whether what's the, let's say, what's the time, or what's the how to put that, in which way it actually tends to what we have to what we want to obtain. So what's the accuracy? How accuracy increases with the number of qubits? Because for some small number of qubits, we're gonna be able to actually probe this problem, to actually simulate this, but then it's not useful. So this might be done as like this accuracy probing only.
So thank you very much for your talk. I have a question about multiperiodic Hamiltonians.
Yeah.
Do you think that it is possible to, for example, enlarge a system by few qubits, which plays a role of a clock, and which of them is evolving with some time corresponding to one of the frequencies, so that you encode kind of this periodic behavior inside the Hamiltonian, which in turn globally will look like non-local one?
Could you repeat your question? I don't think I got it fully.
So imagine that you enlarge your system with qubit, which evolves with some given frequencies omega j, and you divide your Hamiltonian into some H0 times K0 state, times projection of K0 state, plus H1 times projection of K1 state. So while this ancilla clock qubit evolves, you switch between Hamiltonians. And my question is whether do you believe something like that may be useful into tackling this multi-periodic Hamiltonian?
Yeah. Okay. So I think what you point at is basically what they have found out in some sense, because the way to solve this problem is to encode, to go into the other space. So let's say this is this Fourier space. You actually decompose your Hamiltonian, and then by going into this other space, which is either Fourier or clock space or how you wish to name it, then in this larger space, the whole problem ceases to be time dependent. So basically, that's like a clever trick to get rid of this time dependence. And then, since you get back to time dependent case, in this sense, well, you enlarge your system, but you still take into account this linear, and you still get this linear optimal dependence in time.